Hello everyone, it's me, Mr. Younger again. I'm here to solve a potential conservation of energy problem regarding clutches. Let's get started by sharing my iPad screen. So, you see the question here. It says, on a manual transmission, you push in the clutch, change the gear, and then as you release the clutch, two discs, one spinning and attached to the engine, and the other essentially still, come together. If you treat both discs as the system, the net torque on the discs is zero. If the spinning disk is spinning at 1,000 revolutions per minute, notice I put a zero with an underscore after the decimal place. That's just to show that all of the three zeros and the one are significant digits. But it says if the spinning disk is spinning at 1,000 revolutions per minute and its mass and radius are 5 kilograms and 10 centimeters respectively, what is the rate of rotation of the two when they stick together? The initially non-moving disk has a mass of 8.75 kilograms and a radius of 10 centimeters. So that's the problem we're going to work. And believe it or not, you can actually work it as revolutions per minute. You don't have to actually convert it to radians or anything like that. What we're going to do here is go ahead and write solution. And what we're going to do for this solution is we're going to realize that the summation of the torques is equal to dl dt. And since they told us that the net torque on the system, when you treat the system as the two-hole disc, the net torque is zero, that means dl dt is equal to zero. And that means that L is equal to a constant. And that is, L being a constant, is the definition of conservation of angular momentum. Now, the angular momentum L can be written as the moment of inertia times omega, and we know the moment of inertia for disks is 1 half mr squared, and all we have to do is now calculate the initial momentum, which would be L sub I is equal to 1 half the mass of the spinning disk. Actually, I'll subscript that S for the one that's spinning, and the radius of the spinning disk. These two are actually the same, so I'm not going to subscript that at all. And then the omega 1, where omega 1 is equal to 1,000 revolutions per minute, is the initial angular velocity. We have the final angular velocity, L final, is going to be I omega as well, but in this case it's 1 half m 2 for the second spinning disk times r squared times, in this case it will be, actually both of them will have the same angular final velocity, so I'm going to call that omega f. And then the other one will also still exist, so that'll be 1 half m s r squared with the same omega f. So you can actually put these two together as 1 half m2 plus ms times r squared times omega f, and then we can just set them equal to each other. When we set them equal to each other, what we get is 1 half, actually I'll set the initial first, so 1 half m sub s r squared omega 1 is equal to 1 half m sub 2 plus m sub s times r squared times omega final. And now in this case, you can see, because I wrote it this way, we can see that the 1 half is going to cancel out with the 1 half, and the r squared is going to cancel out with the r squared. Not only that, you can see that if I multiplied W1 by some conversion factor between revolutions per minute and radians per second, say, then if I did the same thing to the other side, then those conversion constants would cancel each other out. So there's really no need to actually do any conversion, because obviously we could keep it in revolution. Excuse me. We can obviously keep it in revolutions per minute. So let's go ahead and plug the numbers in as they are, and we'll solve it. And that's not normally the way I do it. I like to solve for the variable that we want to solve for symbolically first and then put in the numbers, but I'm going to do it sort of the way that most students do it. Most students probably wouldn't even call it the 1/2 and the r squared canceling out on both sides either, because that's a very easy thing to miss when you plug all the numbers in initially. So I'm going to go ahead and write in the numbers. We have 5.00. Sorry about that. That's in red. We have 5.00 kilograms is the mass of the spinning disk, and we have 1,000.0 revolutions per minute is the omega. And then on the other side, we have 5.0. Actually, I should put it in the same order as I wrote above. So I'm going to say we have 8.75 kilograms plus 5.00 kilograms, and then all of that is times omega F, which is what we're looking for. So just to remind ourselves, omega F is the question mark. So we can find that omega F should equal to uh, 5.00 kilograms divided by, if we add 8 and 5, we get 13.75 kilograms. And all we have to do now is multiply that by the 1,000.0 revolutions per minute, and you can see automatically the omega is going to come out in revolutions per minute. So this turns out to be 5 divided by 13.75 gives me 0.363636 times 1,000, which gives me 363.64 revolutions per minute. And of course, we only had 3 sig figs, so the 6 and 4 are extra digits. And that's it. That is a example of conservation of angular momentum as applied to a typical clutch/transmission mechanism. I hope that's helpful to you. Have a good day.